Hello everyone, welcome to the channel Vidyut Yoga. In this video, we will discuss about closed loop speed control of switch reluctance motor by using voltage PWM control. Before starting the video, those who are new to this channel, I request please subscribe the channel so that you will get updates about latest videos uploaded on this channel. So we'll start the video. So as discussed, we are going to discuss the closed loop model of switch reluctance motor. Okay, and we'll do the analysis, or we'll check the response of this switch reluctance motor. We know that switch reluctance motor, as the name suggests, actually these motors work on the principle of variable reluctance, like the tendency of the rotor to align with minimum reluctance position is nothing but working principle of switch reluctance motor. Then according to the construction, there are different configurations of switch reluctance motor, like 8 by 6, 6 by 4. That is 8 by 6 means 8 is stator number of poles and 6 are rotor number of poles, whereas 6 by 4, that means 6 is the stator number of pole and 4 is the rotor number of pole. So here, as this model shows, we are going to discuss the model of 8 by 6 switch reluctance motor, like 8 are the stator number of poles and 6 are the rotor number of poles. So for the practice, you can select the available model switch reluctance motor model in the MATLAB software. Otherwise, you can customize your model by changing the various parameters, like here the switch reluctance motor parameters, like stator resistance, inertia, then friction, initial speed and position, sample time. Then in case of the model, unaligned inductance, aligned inductance, saturated aligned inductance, maximum current, maximum flux linkages, etc. That is, you can either select the model from available library or you can customize your own model. So now we are going to study the closed loop speed control of this motor with the help of the voltage PWM control. So in case of the switch reluctance motor, actually in the response we want to check the various parameter. For that purpose, here scope is connected, like we are interested into observe the characteristic for voltage, flux, then current, then torque in Newton meter, and actually speed is in radians per second. So it is multiplied by gain having 30 by PA value, so that this speed in radian per second, it will be converted into the revolution per minute. Then theta, which is given in radian, it is multiplied by 180 by pi gain, so that it will be converted into the degree. So I repeat, we'll check the voltage, flux, current, torque, speed and theta characteristic as an output. For that purpose, we have connected scope here. Then we know that in case of the switch reluctance motor, apart from the controller, we need to control the commutation pulse we need to use the commutation pulse generator to measure the pulse given as input to the each winding, and through the rectifier we provide the supply. Like here we have connected the DC voltage source having the voltage of 100 volt, and that DC supply is given to the asymmetric converter. So since this is this switch reluctance motor having total 8 number of stator poles, so what will be the number of phases? 8 divided by 2. So this is 4 phase switch reluctance motor. So for that 4 phases, we have designed the asymmetric converter. So when I double click on it, it will show the geometry of asymmetric bridge converter for 4 phase switch reluctance motor. Okay, so like this supply is given to the phase A, then phase B, phase C and phase D. Okay, so this is the asymmetric bridge converter through which supply is given to the each phase. Now we need to, in case of the switch reluctance motor, actually what we do, we excite the one winding at a time, and step by step we excite the other windings like phase A, then phase B, then phase C, and then phase D, and according to the tendency of the rotor to reach to the minimum reluctance position, this rotor rotate and switch reluctance motor operate, and hence the excitation of each phase is also controlled with help in case of a symmetric converter. And for the controlling the pulse, here we have designed the commutation pulse generator, like the pulse which is given to the gate A, gate B, gate C, gate D, that means for phase A, phase B, phase C, and phase C is controlled with the help of the commutation pulse generator. And in this case, actually for this 4-phase motor, we are using the step angle of 15 degree, that is for 0 to 15 degree phase B will be excited, then for 15 to 30 degree that is phase C, for 30 to 45 degree phase D, and for 45 to 60 degree phase A. Okay, and here for this commutation pulse generator we are using the turn on angle of 40 and turn off angle of 55. That means advance angle is 5 degree, because actually it should be triggered at 45, but we are triggering at 40. That's why we can say that advance angle is 5, and dual angle is nothing but a difference of turn off angle and turn on angle, which is 15 degree. Okay, so for this case the advance angle is 5 degree, dual angle is 15 degree. So that here, that means turn on angle is 40, turn off angle is 55, that is shown here. Then here for closed loop control, what we are going to do, this rotor position is considered in case of the commutation pulse generator. So feedback from the rotor position is given to the commutation pulse generator, so that according to the position of rotor, that pulse will be given. Then for monitoring the speed of the motor, here we have connected the display to measure the actual speed of the motor. Now for making the closed loop control, here actually we are using the speed controller. So this actually total blocks comes under the speed controller block, but here for the detailed explanation I have not converted it into the single block. Here we will consider one by one block. So here for the speed controller, as we are going to voltage going to use the voltage PWM control method, that is PWM means pulse width modulation. So here actually we will control the width of voltage pulse, whereas amplitude and frequency will remain same. So for that purpose, here we have one block, sum block having minus and positive plus sign. Here the input to this plus is nothing but reference speed, like right now the reference speed is 300 rpm, and that reference speed is continuously monitored with actual speed, so that the closed loop model will get completed. And to take the response or to take the feedback for the actual speed of the motor, here we have connected this minus sign here with the actual speed. Okay, that means the difference of reference speed and actual speed is nothing but error. Then that error is given to the two integrals. So here Kp, that is proportional integral, is given, which is having the value of 1.6, and another error is integrated here with the help of the Ki block, Ki gain, which is having the value of 20, and there is another one integrator is connected in series with this integral controller. So, and this output of the proportional controller and addition of integral controller and its integration is added in this block. Okay, and then there is saturation limit. So here saturation limit, upper limit is 1 because the maximum value is 1 and minimum value is 0. Okay, so upper limit is 1, lower limit is 0. Okay, so this is the speed controller block, and if there is any error, according to that signal will be generated and which will be given here. Then here this signal of the speed controller will be controlled with this repeating sequence block. Actually this repeating sequence block is having two parameters, time values and output values. Okay, here output values is either 0 and 1, whereas time values is depending on the frequency, like here 0 and 0.001, that means the frequency is of 1 kilohertz. Okay, 0.0001, that means frequency is 10 kilohertz. Then 0.002 hertz, that means frequency is 5 hertz. So this frequency is depend on the speed which you want to control. Of course, as the frequency increases, the speed increases. So right now I have selected the frequency of 1 kilohertz. Okay, then this frequency or this signal is continuously controlled, continuously compared with signal from speed controller. Okay, and whenever this signal is less than or equal to this signal, then there will be output will be equal to 1. Then this output signal is continuously is having the AND function, logical AND function, with output of this commutation pulse generator. Okay, and then that signal is given as an input to the asymmetric converter. That means here the pulse will control the pulse of voltage or the width of the voltage pulse here, and according to that the input is given to the asymmetric bridge converter. And here regarding the load, here we have connected the constant load torque of 5 Newton meter. Constant load torque of 5 Newton meter. So if we do the simulation, then we'll get the speed. For example, suppose we want to control the speed to the 300 rpm, then we'll do the simulation, then we'll get the results, and in that results we can observe the voltage, flux, current, torque, speed, and angle in term of the output. Okay, so here we can say that speed is getting up to the 300 rpm, because we have given the reference speed to the 300 rpm. And so if we go through the characteristics or the output response, then we'll discuss these characteristics here. Yes, so this is the voltage curve, and these are the flux characteristic. See here, and this is the current characteristic. If we go through the characteristic, it is observed that the starting current is too high. As compared to the normal current, because we have not connected the current limiter. So if we use the current limiter, then you can control this current also. So again I repeat, for this controlling this current, we need to use the current limiter in the loop. Okay, then this is the torque. Since current is high in the initial period, the torque is also high, and then it becomes it decreases to its normal rated value. Since we have given the speed reference speed 300 rpm, so initially that speed is more, but then again it becomes stationary equal to the 300 rpm. And here this angle, the rotor angle, it goes on increasing. So this is the output characteristic for different parameters. Now what we'll do, again we'll change the speed. For example, suppose I will change the speed to the 250 rpm, then I apply it, and again we'll do the simulation. Then you can observe that speed will be, speed should be controlled up to the 250 rpm. So here you can see that speed is controlled up to the 250 rpm. Okay, so in this closed loop model you can achieve your desired speed, okay, by controlling the voltage pulse width. Again, if we go through the characteristic, this is the voltage characteristic, flux characteristic, current characteristic. As we have discussed, the current torque is initially high, then it becomes equal to the rated value. But since we have given the speed, reference speed to 250 rpm, hence again speed is becomes constant at 250 rpm value. Okay, that means in this model we can control the speed by controlling the voltage pulse width, and it is closed loop model. Thus you can design your switch reluctance motor as per your requirement, and then you can check the performance by controlling its speed, or by making the closed loop speed control model. Okay, I hope the concept is clear. But if you want to reduce the current value, then you need to use the current limiter. Okay, so I hope the concept is clear. I again request those who are new to this channel, subscribe the channel so that you will get the updates about latest videos uploaded on this channel. So till then, bye bye, happy learning. Thank you.